everybody. I'm Dr. Scotty Horey, a faculty member at the Music School of Delaware, as well as endorsed artist and clinician for Sabian cymbals, Vic-Firth sticks, Mapex drums, and Majestic percussion. Welcome back to Tools for the Journey, and here we are at episode 3, which is entitled, What is Science? And Basic Research and Inquiry Skills. So once again, my goal with this lecture series is to just introduce you to some of the most important large-scale disciplines of human thought and human inquiry as they've existed in world history and human history. And we're going to talk about science today. And again, I want to clarify, we're not going to talk about any one given scientific topic or my opinions about science or science-related issues. I'm just going to try to outline the discipline as best I can for you. Because again, some of you might not know exactly what science is, how it functions, and you might have some maybe bad experience or baggage with the word in some way. So what I want to try to do is just tease it out face value from step one, just so that eventually when you apply this knowledge, you can think with more of a scientific mind. When you tackle some of the challenges of your life or issues in your life, whatever they might be. And of course, I'll say again, just like I did at the intro of this series, is that nowadays science is very important. We have a lot of different opinions. We have a lot of different challenges that the world's facing, a lot of different unique challenges that demand that even the layman knows at least a little bit of how science works and why science is important. So, with that said, let's get started. Let's try to answer the question quickly first. What is science? And I'll start with the Oxford Dictionary's definition, which is, and I quote, "Science is knowledge about the structure and behavior of the natural and physical world, based on facts that you can prove, for example, by experiments or by deduction. And it's also a method of inquiry to learn more. And it's a tried and true method. We'll talk more about the scientific method in a moment. But it's a tried and true method of inquiry that many cultures and civilizations have used since the beginning of human history, or since near the beginning of human history." Another interesting definition that Wilson E.O. Consilience wrote in his book, The Unity of Knowledge, goes as follows. "Science is a rigorous, systematic endeavor that builds and organizes knowledge in the form of testable explanations and predictions about the universe." Now, why is having a scientific perspective on a topic more important than just your intuition? Well, first of all, I should be the first person to say that scientific discourse isn't necessarily the most flattering type of social activity. But when talking about challenging issues, especially in the context of academics or in a class or at a conference or in any type of academic situation or work environment, I would say it's very important to have a scientific perspective. And again, why is this more important than just intuition or personal experience? Because typically science represents a larger body of knowledge. And when you share intuition or personal experience, those things are very valuable. I don't want to be remiss and miss saying that. But in science, we usually call this anecdotal or anecdotal evidence, meaning it's valuable evidence, but it's only reflective of one person's experience or one person's observations. When we use things like the scientific method, or when we look back at scientific records or research, we're looking at huge bodies of knowledge that represent many people's observations in systematic methodological ways about specific problems. And in some cases, we're looking back at a multi-generational history of scientific affirmation about a given topic. So if you're talking about a current event or a problem at a workplace, a complex problem at a workplace, or in an academic setting, in a class, in college, in a lecture, when you're studying your discipline, when you're teaching music, any of these things, it's very important to have somewhat of a scientific perspective, or sometimes to have a scientific perspective. And even if you're not a scientist, and I'm not a scientist by credential either, it's important to be able to adopt that perspective even for a moment, even if you're just dipping into the basics. So the other component of this is knowing how to read statistics. And statistics and looking at data figures is something that you also should know how to do. And again, I'm not going to disassemble the details of that because this is not a statistics class. I'm just going to make the assertion that if you want to have more of a scientific mentality or be able to see things from a scientific perspective, it also involves knowing how to read statistics and data sets. And of course, this is something that came up during the pandemic, especially with the vaccines. All of these public opinions started emerging, some of which more credible than others, some of which clearly reflective of people that knew how to read facts and statistics, and clearly a lot of the problems were because some people did not even understand how to read facts and statistics and skewed them or misunderstood them and developed all kinds of beliefs on all sides of the story. So again, this also means statistics is a peripheral discipline here that we need to know about. And I would say especially in today's world, the pandemic and vaccine usage only being one example, in today's world we have such a diversity of opinions about almost any issue. We have a huge amount of information and data available online, including misinformation and confusing information. And then in the most innocent cases, as simply epistemological diversity. So we have people with different perspectives, different cultural experiences, different training, and they're offering up a lot of different ideas. So it's a very challenging time now to assert the truth. And this is a discussion that's been very popular lately. So one response I would have for that is to simply understand scientific mentality a little bit more and how to look at facts and statistics. And then, like I said, it's up to you to apply these things in your life and the various things that you're thinking about and interested in and working in out in the world. And of course, we're living in a time, I think, in the United States where we want to listen to everyone's opinion, but which is great, but we also have to remember that some assertions, especially if they're about things, let's say in the STEM fields, are simply not as credible as others. Some statements are more true than other statements. So we need to adopt a scientific perspective frequently, not always, but frequently, in order to tease out the epistemological or epistemic value of several statements and place them against one another. There's just no way to solve problems if we don't have the ability to do that. And like I said, I think this is a particular challenge in today's a world of diverse knowledge and diverse opinions. So let's give you an example of this. So why is having a scientific mentality about something, or what would be a case where having a scientific mentality about something would be advantageous or important versus just your own personal experience or personal intuition? And there's only some examples. It wouldn't be 100% of the time. But an example would be, for example, deciding on a treatment plan for an illness that you have. So obviously, something I'm going to mention more than once is you have to consult experts. So in this case, it would be a doctor. But when making an assessment about which treatment plan to put into practice, or maybe what exercise routine or diet regime to put into practice, you need to consult experts, and you also need to look at scientifically how many and who these types of interventions have benefited. Now, if you just took personal advice from one person that you love or care about, that would be valuable, but you can see how it would have its limitations and even risks if you didn't also adopt a scientific perspective to look at larger data pools and know a little bit about how to read those. And if you consult professionals about, which you should, about such things, you also want to have the toolbox to be able to gather all this yourself and to make assessments. And Another point about why this makes sense is that in the case, especially, I'm using an example for medicine, especially in the case of medicine or pedagogy, teaching, or social sciences, frequently when you look at data pools or figures, it's knowledge about a solution or implementation. It represents what helps the largest number of people, or, for example, what has the largest probability of the desired outcome, or the largest probability of the result or of success. And again, that's based on scientific research and large data pools. So if the question is, what medicine might make me feel better, you want to reference that type of mentality. If the question is, what piece of music should this student learn if they're going to get ready for a college audition, there's a lot of work that you could look into to assess that. If you're talking about something within economics, you can look at the data about what particular intervention has worked, what particular intervention has not, and you can look at numerical figures as well as qualitative reports. So the only point I'm making here is that just using personal experience or intuition is valuable in many cases, but it's also limiting and risky even in other cases, which is why we need to sometimes adopt a scientific perspective. So next, what are the various types of sciences? Science is a very broad field. Just like music is, there's a lot of different, very unrelated areas that are subsets of the field. So to break it down, what are the three types of sciences? And there's various ways to put this into words, but what's generally understood is the following three. The physical sciences, so that includes things like physics, chemistry, biology, which is one of my favorites, and environmental sciences. Number two is social sciences, which are things like sociology, psychology, and economics. Number three is formal sciences, and these would include things like logic, or scientific logic, mathematics, and computer science. Next, I'd like to talk about the various types of scientific experiments and the various types of scientific documentation. And this is particularly relevant to the present day because a lot of things are deceptively scientific documentation, but are not. Like, for example, journalism, whereas it can include references and scientific points, it's not scientific documentation. Or someone writing a book and talking about science is not scientific documentation. Someone speaking on a podcast, especially if they're not credentialed in the area, they're talking about science, is not scientific documentation. It's a discussion about science. So just to look at the very pure, raw facts about what constitutes technically scientific documentation, it includes the following. And I'd like to speak about two of them, which I think are most relevant, especially if you're not going to do a career in science, or if you're not particularly trained in reading science, or maybe it intimidates you a bit. Maybe you think you can't handle the reading. And scientific reading is very challenging to read. It takes a lot of energy and training in some cases. The two I'd like to talk about are review of literature and meta-analysis. And I think these are probably two of the most useful ones, especially if you're trying to gather the professional consensus about a topic, or the professional consensus about the answer to an inquiry or a problem or interest that you have within science. So a review of literature, what that does is it basically is a paper that takes interesting points from that particular question and consolidates them into one readable document. So meta-analysis is the second one, and that's very similar, but usually that's more formalized. So the best ones in medicine would be, for example, Cochrane reviews. And that would be the very large-scale professional consensus about a particular question or particular data point. So let's say you're trying to research, let's use another example in medicine, maybe treatment for skin disorders, for example. Instead of reading one or two papers, which represents one peer review board, one methodology, and one experiment, and maybe 200 or 300 patients, a meta-analysis will look at that study and then maybe even 100 other studies like that and consolidate it into a large paper to make an assertion about the subject matter at large based on what we know. So as you can see, that's drawing on a lot of information to make pretty well understood, tangible conclusions that you can work from and use as a reference. So like I said, if you're not going to do a career in science or you're not a scientist, doing reviews of literature or looking for reviews of literature and or meta-analyses can be very valuable. And again, depending on what topic you're interested in. For a lot of people lately, it's been environmentalism and medicine, but it could also be in chemistry and engineering, any of these kinds of things. There's other different types of experiments that are important. Basically, experiment is something that involves a hypothesis, a research, experiment, analyzing data, and then compiling the results. We'll talk more about that in a minute. And trying to clear up any methodological problems that might interfere with the accuracy of the results or any discrepancies in the experimentation process itself. So there's many different kinds of experiments and studies you could do. In medicine, we look at various things like, for example, a clinical trial, a randomized control trial, a double-blind study, which is an interesting one because the experimenter and the experimented on do not know the A from the B. So there's very little error that can happen methodologically with a double-blind study. And then there's other things like case studies, where you look at something very specific that happened, like an isolated incident or like one person's situation, and you try to disassemble it detail by detail, and you use that as a way to learn more about the subject matter or the question at hand. So that's an interesting one. And then another interesting one that I put down that I like is animal models. So we've learned a lot about, for example, human biology by studying animals, because we know there's a lot of similarities. So we also use animal models, given they're treated correctly during the experiments. That's a very big discussion in the scientific world, to learn more about other things, including humans. So let's just do a brief history of science. And we're going to go pretty far back in human history to trace some of the beginnings here. So the Bronze Age of Egypt and Mesopotamia was from roughly 3000 BC to 1200 BC. And this was a huge period for the beginning of science. Their contributions to mathematics, astronomy, and medicine entered and shaped the Greek and ancient Roman natural philosophy from the classical antiquity. And classical antiquity is, of course, one of the next most important periods in the development of Western civilization. The scientific revolution was a series of events that marked the emergence of modern science during what we call the early modern period in history, when developments in mathematics, physics, astronomy, biology, human anatomy, and chemistry transformed the views of society about nature. And the scientific revolution took place in Europe in the second half of the Renaissance period, a little bit later, with a 1543 Nicolaus Copernicus publication, and here I go with my Latin pronunciation, De Revolutionibus Orbium Coelestium. Latin pronunciation is a little rusty, but that translation is On the Revolutions of the Heavenly Spheres. And in addition to that, Isaac Newton's 1687 publication Principia, which formulated the laws of motion and gravity. And subsequently, after those two texts, we eventually see the beginning of the Age of Enlightenment, the next very important period in European history that shaped all of Western society intellectual prosperity and societal prosperity. So, new knowledge in science is advanced by research from scientists who are motivated by curiosity about the world and a desire to solve problems. And there's a huge amount of utility that scientific discovery has to human flourishing and society and economy. Contemporary scientific research is highly collaborative and is usually done by teams in academic and research institutions, as well as government agencies and companies. So all three of those sectors could have scientists employed and supported in their endeavors. And part of this also is the establishment and upholding of organizations that manage professional journal publications in credible journals, some of the most credible being Science, Cell, Nature, the New England Journal of Medicine, and Lancet. And each of these journals has a peer review board which scrutinizes each submission before publication, as any journal does, but these journals have a long-standing history of excellence and a history of the highest standards. Developments in science have aided in improving the quality of life of the human species across history. In the first half of the century, the development of antibiotics and artificial fertilizers, for example, improved human living standards globally. Another example would be the discovery of insulin at the University of Toronto in 1921. And that discovery is responsible for saving my life. As a type 1 diabetic, I take insulin, pharmaceutical insulin, every day. Very little of it at that, because I control it with diet and other things and exercise. But without that scientific discovery, type 1 diabetics passed away from complications very early in their life. So I'm very happy I'm here talking to you on this computer video, thanks to that scientific discovery. In the early 19th century, we had John Dalton provide the modern atomic theory in atoms, as well as conservation of energy, conservation of momentum, and conservation of mass. And of course, the steam engine was a gigantic discovery that sparked the beginning of the Industrial Revolution, very important for economics, in U.S. history economics, and that was because of a scientific discovery. Early 20th century included classical genetics, and now we have epigenetics, which is an expanding field. We had Albert Einstein's theory of relativity and the development of quantum mechanics to understand more how the universe works in length, time, and gravity. And it didn't stop there, obviously. 20th century also combined with communications study and satellites led to the revolution in information technology and the rise of the global internet and mobile computing, including, of course, development of the smartphone. 21st century, we had even more, better understanding of the human genome, and of course of genetics and medicine, particle physics, and black holes. And not only do some of these things have social and economic utility directly, they improve quality of life, but they spark a stronger sense of wonder and curiosity, which, of course, being someone from the humanities, I would argue is just as important. I think science is, this is maybe a personal opinion for a moment, I think science is one of the fundamental things, represents one of the fundamental things about the human spirit, which is the desire to learn more and to be curious and to expand. So let's talk a little bit more detail about what the scientific method is. And let's take a look at this graph here, this graphic. And what you see at the top is observation or a question. Second thing is research the topic area. So a little sort of background homework. The third would be hypothesis. So then you have to form a projected answer to your question. An assumption. And then you have to test that hypothesis with an experiment, which of course is designed with good methodology. And after that, you can analyze the data that you gather. And then, of course, all of this is useless without reporting the conclusions in some type of clear, coherent way, ideally in a publication, whether that be from a journal or in a book or in various online resources. Ideally with one of the mediums I spoke about earlier, which involves a pretty lengthy process of review and edit and revisions, et cetera, et cetera. So you have to report the conclusions in a way that's honest and clear and useful, so that when the second person attempts the same scientific method, they can draw on your work to keep the expansion and the acquisition of knowledge going forward. Use of scientific method must also include mathematical models and statistics, especially in the gathering of results from the experiments, analysis of the data, and this brings me back to what I was saying before about knowing a little bit about statistics and reading and writing data sets and graphs. Okay. There's a couple of really important issues that have surfaced, that have been issues for probably over hundreds of years, but especially in the past 6 to 8 years, especially the rise of the internet. One of those would be pseudoscience. And this is somewhat of a controversial topic because it's difficult to discern what is science and what is pseudoscience. But there's been many cases of pseudoscience, especially in the past 6 to 8 years, some of which being some anti-vaccine activism, flat earth science, ghost hunting, quantum mysticism, and other similar disciplines. And some of these have been problematic, and sometimes they have political or commercial incentive, especially towards a population that does not have the ability to understand the problems of scientific legitimacy or problems in the bias of the methodology. So we need to be very careful about pseudoscience, or sometimes what's called in medicine quackery. So let's talk about the philosophy of science. There's some different schools of thought here. The most popular position that scientists take is empiricism, which holds that knowledge is created by a process involving observation, scientific theories that generalize observations. Empiricism generally encompasses inductivism, which is a position that explains how general theories can be made from the finite amount of empirical evidence available. So think of it as kind of a technique of deduction. And of course, if something is deduced empirically, we could say that it's true, and we'll get into the nature of truth in further lectures as a very deep question. What is truth? You could say something that's been shown empirically is the truth, but of course it doesn't negate the possibility that there's some missing information. Empiricism is just a way of deducing the best truth that we could come by about the given question, given the data available. So let's move on and talk about a somewhat broader topic than just science, but it has to do with the scientific mentality, which is investigating a topic skillfully. And of course, with the rise of the internet and the expansion of things like podcasting and authoring and intellectual diversity, this is a huge challenge nowadays. If we have a question or we're interested in a topic, especially a scientific topic, how do we investigate that topic skillfully? How do we do so in a way that's not clumsy? Or how do we do so in a way that doesn't lead us to misinformation or lead us to confusion or lead us to be misinformed? Or maybe it's something that's over our heads. Maybe there's a few topics we need to learn about to get the basics down before we tackle whatever interest or question we have, which, of course, as an educator is something I think about frequently. And this topic has a lot to do with the education lecture. So I would go back and review that or watch it if you haven't already, which is episode 1, What is Education? So investigating a topic skillfully. First thing I'll say is be sure to look up and review someone's credentials if you're taking information from them. Now, this could be a book, YouTube, article. It could even be someone in person. You have to know who's giving you the information. And it's very popular nowadays for people to step outside of their credential and to make assertions that they're not qualified to. And all sources will have different types of epistemological value or epistemic value and have varying degrees of credibility. And no one's exempt from this. My area of direct expertise is music, and in particular percussion. But even with that said, if someone asks me a question about congas, which is a type of percussion instrument from Cuba, I can just give them basics because it's not really an area of particular expertise for me. I don't know a lot about that specific area. So if I give someone some information about congas, I have to make sure to tell them that this is my perspective, and actually there's people that I can tell you know a lot more about this given topic, even though technically my area of expertise is in the larger area of percussion and music. So what I'm saying is that no one's exempt from this idea of credential being on a scale, or on a spectrum, I should say. And just to bring up what I said earlier, that's why when you read about a scientific topic, it does not make any sense to not read something that is peer-reviewed. Some people like reading journalism and sort of journalized science, but if you have the ability to read it, you feel like your reading skills are ready for it, you should go directly to peer-reviewed literature with a good editorial board. And if you know something about that, you can also start to discern what journals have good editorial boards and which journals maybe not so much. But that's a little more of an advanced topic, especially if you're writing a DMA thesis or a dissertation. So is someone's information well-cited? What are the quality of their sources? I'm so impressed. I'm so flabbergasted sometimes to see seemingly very qualified people give information either in a book or in a podcast, and they don't list any sources at all. So this is something that you want to be aware of, especially if the claims made are masquerading as scientific claims. You really want to see if they're well-cited. It's a good mark of trust and integrity when you open up a book and you see that there's a large number of sources or citations. And, I don't want to be remiss in saying that there's huge value in personal opinion and anecdotal evidence and personal narrative, as well as sharing things like relational dynamics and emotions and things. I don't want to discredit those things. I do want to say, though, that it's a different modality of interaction, and it really depends on what the subject matter is and what the conversing is in that particular time. They're just very different, and we have to see when some of them are more appropriate and when some of them are less appropriate. And we want to see that on a spectrum, too. Okay. So I'm going to bring up something that I said also during actually both episode 1 and episode 2 so far, which is the value of knowledge. So there's many different kinds of knowledge, like I mentioned, which I just mentioned. And scientific knowledge really is only one of them. Probably one of the most important types of knowledge, especially nowadays with with the magnitude of some of the problems we have in front of us as a society, as a global society. But it is one genre of knowledge, or rather, it is one mechanism of knowledge acquisition. And of course, this is one of the big points in my doctoral thesis because as a performing artist and as a teacher, I constantly make references back and forth to scientific knowledge and phenomenological knowledge, which was firsthand subjective narrative. So that was one of the big challenges in my thesis. And like I said a moment ago, it is possible to combine these different types of inquiry and different types of narrative together. You just have to be aware of them. So what we're talking about is awareness in education. It's definitely not seeing one thing as more important than another thing. And the other thing I'll say is I'll kind of go back to that Martin Luther King quote, and I'll say that knowledge alone is useless. So don't be deceived at the face value of simply acquiring more knowledge. Knowledge should be the basis for establishing action items, new or modified routines, behaviors, and applications that are healthy and useful and virtuous. And of course, we all, as social animals, have to engage in relationships. And relationships aren't about the use of data or scientific data. Relational dynamics are also an integral part of prosperous human activity. So again, all these things can work together in a dynamic system. Relationship dynamics, emotions, with also the backpack of scientific knowledge at our side. And I'll spell out again in as clearly language as I can that knowledge and data should be combined with values and morals and a set of well thought out axioms instead of having these things take shape accidentally. Values and morals and purposes should be well meditated and very intentional, so you have a place to apply the knowledge and data. Now, I don't quite have the explanation for this, but I will say that in my observation, I do think there is a small subset of people that acquire more knowledge as a procrastination effect. I know I can fall into that role sometimes. And we do have to remember that knowledge and behaviors, or emotive behaviors, are completely different things. We need to and I'll say again, we need to let our scientific knowledge shape and change our behaviors and see our behaviors as constructive and informed by the knowledge. And sometimes simple behaviors and conveying an idea with simple emotion is more useful than more data. It just depends on the context. There's a principle in science called Occam's razor, which some of you may have heard of. It's well known in kind of pop science, which says all things considered, the simplest explanation sometimes is the best one. So sometimes acquiring more intellectual knowledge or data about a given topic isn't necessary. Frequently it is, but sometimes it isn't. So in terms of a review, let's just go back and see what we've talked about. The title of this lecture was What is Science? So we did an introduction. We talked about some various definitions of science from credible sources, the different types of science, different types of experiments you can do. We talked about journals and scientific documentation. We went through a brief history of Western science. We talked about the scientific method a little bit with the graphic. Talking about good research skills and what it means to investigate a topic skillfully. We talked a little bit about epistemology and the value of knowledge and some of the challenging dynamics that we have as humans interacting between science, data, and more relational, emotional dynamics. And the difference between knowledge and behavior and the relationship between knowledge and behaviors. And now here we are at action items, the very last part of today. And I'm going to credit my awesome girlfriend, Jennifer Lang, for inspiring me to add one of these at the end of every episode from this series. Like I mentioned a moment ago, knowledge alone is useless. You have to include motivation and behavior, and you have to get up and do something with your new knowledge, even if it's just a small first step. So here's a few things you can try in your own life now that you know a little bit more, hopefully, about what science is and why it's important and how it works. first thing I might encourage for you is to get a library subscription. There's a lot of research that goes into the importance and the efficacy of simply reading paper books and placing yourself in a state of concentration and in a behavioral routine of reading paper books. So you can do that, but you can also, with a library subscription, have access to huge digital databases of online journals, many of which are scientific. So I want to encourage you to do that. If you're a college student or college staff or faculty member, you also automatically have access to huge digital databases of journals and papers. And the next thing I can ask you to do is read general public audience books by people that have credentials in science. So you don't have to pick up a science textbook to learn about a scientific topic. There's a lot of really great books that are designed to be read by the average person, by the layman, by scientific authors. Let me just try to think of some examples off the top of my head. This Is Your Brain on Music by David Levitin. This is a good example. It's a very easy read. And he's an authority in music, although it's not an academic textbook. So there's plenty of ways to get your nose into understanding and thinking scientifically a bit more without getting into something that is not pleasurable to read or too difficult to read. And I'll say again, learn how to interpret data. Try taking a statistics class, or try learning a little bit about statistics. What does it actually mean to know how to look at all those data pools? I'm quite surprised actually at some of the government websites like CDC, WHO, or any of the .gov sites about health and wellness are really challenging, and I have a doctorate, are really challenging to look at the data unless you have some education in that area. So try learning a little bit about that by taking a statistics class or learning from someone who knows how to read scientific literature or data, just to get the basics. The last thing I'll say is if you have a scientific inquiry, have a discussion with an expert. Just be careful as to who you speak to, because many people have sort of pathological concepts of scientific topics, but they don't actually have the training. So if you have a question, be sure to consult an expert. A lot of people are talking about health and wellness and illness now because a lot of people are very unhealthy. And so there's many doctors with different credentials that can speak about these different areas, and it's important that you find the right one in that case. And that goes to just about any scientific topic. All right, so in conclusion, remember there's not many sources for this lecture because I'm just bringing you through the basics, outlining the discipline. We'll get more into specific areas in the future at scottyhorey.com and Scotty Horey on Tributary. But with that said, I do have a limited amount of sources that were needed for this lecture on the YouTube description and the Tributary description. Thank you so much for watching this episode. This is episode number 3, What is Science? And we're going to go ahead and move on. Please, of course, stay tuned and visit scottyhorey.com, Scotty Horey on Tributary. Thanks so much for your time. I hope you found this useful.